And it is going. Okay. So how do I turn it off? Hopefully that'll be captured now. Okay. Anyway, so today we're going to talk on radiation physics. The main goal of this is looking towards, in particular, X-rays, because we're going to talk about X-rays and X-ray CT and how they work, so we have to kind of understand what's going on here. But that's not going to be the only time it's going to matter to us. So the same stuff's going to come back again several times. One of which will be when we get to PET scans, right? So we'll talk about how they work, and that's positron emission tomography. So we have to talk about basically nuclear decay and positron emissions and what they produce. So that's going to be another case where the same type of stuff's going back. I'm imagining a decent chunk of this is, at least the beginning parts will be somewhat familiar, but I think we'll fairly rapidly get into some stuff like Compton scattering that you're probably not familiar with. So what we want to look at today is, first off, just have a basis for where all these quantities come, understanding the basic interaction, when relativity kicks in, when quantum kicks in, and how to basically get the equations out of those. Physically what they mean, what to kind of expect scale-wise on a lot of these different terms, which terms are going to be important and which aren't. And a basic understanding of how it functions. So that's kind of the general overall goal for all this. So I got to pretty much start with atoms 101. So this is one that I think you're probably pretty familiar with. But we want to hit a few things, may or may not be as well known. So anyway, right, we're all familiar with atomic number, right? So why do we care about atomic number?
So many protons it has.
Okay. So that gives us protons, which gives us some idea also about its mass. It's not exactly, but there is a relationship, light and heavy versions between the atomic number and the atomic mass. We'll get to that one a little bit more when we go on. But if you look at light ones, they're pretty proportional. When you get to heavier ones, there'll be about 60% more neutrons than protons in them. Right? So it's kind of important for that, right? Neutral atom, we also have electrons. Why does that matter to us? Any reason we care about electrons?
Balance the charge.
Okay, so they do balance the charge. That's very important to us. Some of our radiation will actually be ions. So dealing with the ionized version, knowing what we have is going to be fairly important. Right? Is there anything else important about electrons?
It will be excited by radiation.
Exactly. And they themselves will be the source of a lot of our radiation emissions from this. There are other ways you can get some of these radiation emissions, but a lot of it's actually going to be from the electrons and the structure that they form. So therefore, having some idea of the number of them, which can tell us about the shells and how they fit in, their position, will give us some idea of the energy range that goes on. I make the comment also that it's isomorphic to the symbol. So a lot of times you'll see, where it'll say like carbon 612, right, as a particular isotope, right? So I've got carbon over here, right? So the atomic number Z is 6. That is a one-to-one relationship between the letter, or letters in certain cases, radon, radium, stuff like that, right? But essentially, if you know the symbol, you know the atomic number back and forth, but not actually totally true with the weight. Right? So that's, it is kind of good to know that we carry those ones through. You can see here, this is that kind of one-to-one zone where the lightweight. So in general, for your stable isotopes, you're dealing with 1 neutron for every proton. So everybody familiar with what's going on here with the shells? Right? Maybe I should even start with orbitals first, right? Orbitals make up shells. What are the types of orbitals that are out there? And who cares about an orbital, right? Yeah, so you see pictures there, right? But I mean, so you could see them, but like, what are the types? What are they? What importance do they carry? What do they generally? I mean, you got pictures of what they look like, but significantly, what do they kind of mean when they're going in?
They kind of determine like how an atom will form molecules and then can bond. So like a one-on bond is usually like an S orbital. We're bonding like a sigma bond, and then they have like pi bonds, which are like a double bond. Or a double bond has like one pi bond, one sigma, and then
Right, but it does have to do with that bonding structure, number one, right? And that becomes important when we start dealing with molecules, because molecules are actually by and large very important inside your body, right? Which is the lowest energy of them? If S for any level is the lowest that's in, right? And if you look at it, that's kind of the spherical shape that's in them, right? That's not actually the reason for the letter, but it's a nice memory mnemonic, right? So you get these kind of spherical. How many electrons in it? Up to two. What are the two? There's something. Yeah, up and down. What's significant about up and down spin?
It's like the.
Do we really know they're spinning? Yeah, so the only way you could tell is that. So this has to do with one other area that's important to us, which is MRI. This is going to be one of the things that's going to matter to us heavily. That spin that's inside will be important for doing MRI imaging. So that's another kind of important one just to kind of remember when we get these. Right? Okay, so we've got this idea. We've got a spin up and a spin down. Right? Two will fit within it. It's kind of the most compact. So this is the lowest energy state at any particular one of our orbital levels, right? Or it's lower than the other orbitals. So when we get to the shells, it's going to be the lowest for each shell. How about P? What do they basically kind of look like? What's that? Yeah, right. So you get those kind of. And how many of them are there? Three. Why? Right, one aligned to each of the dimensional directions, basically, as a pair that goes in. Right? And we see this obviously inside the basic structure when you deal with your periodic table, right? Because you can actually see how they fill in. Right? We have hydrogen and helium. Those two outside ones are on there, the tallest. That's the S shell, the up and down filling in. Right? Coming across the middle, the next layer that comes in, that's all your P's filling up. Right? So it's also a fairly low energy. Right? How about after that? Right? Yeah, so now we're starting to get into some odder shapes that are going on. Right? So there's usually one that's kind of symmetric that's along, which is kind of like a bunch of stacked pancakes almost. And then there's usually one that almost looks like a checkerboard fill-in. Of every set. So that's what you can kind of see here, right? Kind of stack. You'll see the same thing going in, right? Whether you're dealing with D, here's F, here's G. They all have one that kind of looks like that, kind of stacked together. And then you have the rotating around one, right? And then you start hitting in these ones that start getting kind of more checkerboardy as patterns, right? And these are basically, you're trying to fill in charges. They don't like each other. They want to repel. So what's the basic shape you can make so they have the least problematic interaction with each other, right? Now, those orbitals that come here, not all of these are equally easy to fill, right? So we're kind of easiest and off we go. I want you to know something careful about this one. Generally, if you look at these type of charts, right, you're going through, right, K, L, M, N. I'm presuming you did the letters, right? Sometimes people just number them first, second, third, fourth, so on and so forth on the shells. Do I fill all one shell in before I move to the next?
No.
Yeah. Where's that kind of break point happen? Right? right? Because you will completely fill up the M through the third shell, right? Once you get through that third shell, now it's going to start to become more and more difficult to fill them in. Technically, you still fill N, but you don't all the way fill O, right? So there's 2, and then 8, and then 18, and then 32, and then 50. But notice, for any of our stable items, we never filled the rest of those in, right? Anything out there is unstable. Okay, so theoretically, they're there, but these are higher energy than filling these in, right? The S of that next layer up is actually less than those are. So it will tend to fill up some of those outer layers. That becomes important for some of our systems, right? And that's kind of one of those big breakpoints. So a lot of the stuff we're going to deal with is down in this zone, right? Most of your organics tend to be there. You tend to be much more unstable out there, so when we deal with radioisotopes, you're going to be on the much higher end. When we deal with the PET scans and things, so you're going to be higher up. So kind of having some feel for where that goes. Most of the time, you'll only see stuff labeled out to here, right? Which you can see because pretty much the standard ones we're going to deal with are going to be in that zone, right? The organics are going to be way down here, usually the first 3, right? A lot of the metals like titanium we use and stuff like that will still fit nicely within that structure. Okay. So that's just why I wanted to kind of pull off from there, right? The atomic radius is nice, but it's we'll kind of ignore it. It is important when you deal with electron density, but won't sweat it too heavy. Okay, so this is a brief chart of atoms we want to deal with atomic mass, and this gets into decay structures. All right, so there's some standard behavior for all of them. All right, so I listed the decays here, but without looking at them, right? The 2 most popular, right? Alpha and beta. Those are how they're discovered. They got their names actually from them. Anybody remember what alpha decay is? Yeah, so it's basically a helium ions core, right? That's not actually how you get them, but it's trying to dump that kind of even ratio of protons and neutrons. Where do you think that would be useful? If you were just considering all the realm of every possible atom, that's really what's drawn over here. Right? The black line is the stable ones. Okay? These are ones that we know what's going on, and beyond that is kind of theoretical. Right? They don't happen. Right? So we don't really have measurements on them. But where do you think that would be useful for? And basically having a core throwing out the helium ions nucleus. Too big, right? So that's really the idea here. You'll notice I put this here. If your atomic number is bigger than 83, they put it at 82 here. It's a little bit arguable where it goes, because if you look up, the question is really, if you put it here, they're catching this little bit of yellow. If you put one over at 83, you got this whole big line going up to catch both of these sides. It's not like a magic line. You'll see a little bit on the outer edge here. All these yellow ones here are all alpha decays. But basically what they're telling you is it's too massive, so it's just moving you down in this direction. Right? So this is, I put an A here region just to say that's the alpha decays. And PowerPoint didn't make it easy for me to put Greek letters in. So someday I'll go back and put that in. But anyway, you can kind of see, think about your areas, right? Alpha decays are going to happen on those really massive areas. And you can see it can happen below that level, or even a few down here, but usually it tends to be in that zone where you're too heavy and you're trying to move down rapidly, right, to get to a smaller, more stable core. That's it. So that's kind of the purpose of alpha. It was actually the first ones they discovered. That's how it got the name alpha. There's nothing magic about it. When people were doing it and firing stuff at gold nuclei, right, they got these emissions and they said, oh, this is the first type of emission we got. It's got a standard pattern to it. We're going to call it alpha because it's the first one we discovered. Right? So beta, right? So beta, I'm ejecting an electron. Right? This is sometimes also called beta minus. You'll see it put because it's negatively charged. So anybody, have you all seen beta decay before? Have you seen alpha before? Have they talked about it in physics? They talked about it, but it was a while ago, and who cared? I just honestly trying to find where we're at, right? Do we remember the idea of beta? Yes. So you got too many neutrons. That's really the situation, right? So you need to get a proton. So you can kind of think of it, if I took an electron and a proton and shoved them together, I'd get a neutron. Not totally true. There's also a gamma that comes off of this, but right, essentially that's, you know, the basic idea that's in there. Right? So in this particular case, a beta decay, I've got too many neutrons. Right? So beta or beta minus, you can see this whole region up here, you can see the upper part here, that's all the beta minus. So basically they have too many neutrons, so they're kind of trying to walk down this way. So they're saying within the same Z, it's staying the same type of, you know, or actually I should say you are converting an increase V by 1, right? So I'm kind of going, I should say, over this way, right? Z went up. So beta minus will take me across here, trying to get me to something stable. So wherever I am, I'm converting a neutron, right, into a proton, and this is my, that's neutron count. Sometimes they put A there, right? So this particular one is neutron count, so it's going down on an angle, right? Because you lose a neutron, you gain a proton, so it's diagonal down. Anyway, so that's a beta. Notice there's a beta plus. So beta plus is a more, you know, was a later discovery, and it comes in on a fairly nice connection. Think, right, minus plus, they're flipped. Something that's like an electron, but positive. So what's kind of like an electron, but positive? Positron. It's antimatter, right? Flip things on. So that one's going to kind of go the other direction in a sense, right? So Z will decrease, right? And I will increase my neutrons. That's all. Now, that positron, is it going to last long? It's antimatter, right? So what you're expecting is it's going to go out and it'll either ram into a free electron, right, annihilating, and you'll get two very high energy bursts off here. Just kind of stick this number in your head. The electron's mass energy, right, if you take a look at its rest energy, is about 511,000 electron volts, right, so 511 keV. So roughly speaking, when you end up with this positron going on, you're gonna, you know, essentially it gets annihilated. It usually gets annihilated by running into an electron. So you're gonna get two of these 511 keV gamma rays shooting off in either direction. So it'll travel a little distance and then boom. Right? That's the same type of thing we're expecting when you deal with PET. So just kind of stick in the back of your head. That's a very high energy emission. So when we're doing X-rays, we're nowhere near this. So X-rays, depending on the thickness of your body, an X-ray that's going all the way through a typical person will be anywhere from, say, 80 to 140 keV, ballpark numbers. And then there's one that's kind of at a lower range, about 30 to 40 keV, and that's for mammograms, because you're only going through a smaller section of soft tissue only, no bones. Right? So that's usually how that breaks down. So on the lowest end of any amount of X-ray imaging for a smaller amount of tissue is about 30, and it goes on up from there. Nowhere near about what you're going to get with a gamma ray from those. Right? But essentially you can see all the ones below that stable black line are going to have a beta plus, where a proton turns into a neutron. So they're going to go down one proton, up one neutron, so they're going to go diagonally towards the line. All right? So all of those, you kind of think of this is a manifold of possibilities, and it's a stable manifold in a sense, because even if you're off it, it's going to push you towards the center with those two decays, right? So beta plus, beta minus, those are the big ones, right? The other one you'll get that allows you to do that same thing is an electron capture. So it's possible for you that these are kind of a rare occurrence, but I could have a high energy electron that has enough energy to kind of pound into your nucleus and therefore cause a reaction. Usually they don't have enough energy to overcome and actually come into it, and they get stabilized in orbit. But it's possible in some cases that you can actually have them come in and hit. You get, X-rays coming off them, but essentially it's going to do that same reaction, right? That electron is going to hit a proton and make it turn into a neutron and then release some radiation. So it's going to do that same type of behavior that's on here, right? And you can see some of those, right? Proton and that, right? Again, it happens just down here. Tends to be with the more lightweight ones. It gets harder and harder as you get a more massive one. You got a bigger electron shell around it that's kind of playing interference for the core, so it gets harder and harder to heal. So you tend to see those electron captures down at the bottom. There are a few up though, it's way on the edge, right? That they will sometimes lose enough for you ones that you can kind of get to happening. Particularly that's where things are decaying and shoving a lot of electrons out on their own. So they get shoved out from one nucleus and rammed into somebody else. All right, the other one that happens is what's called a gamma decay. This one doesn't change at all. All it does is if you have a nucleus in what's called an excited state. So imagine it's got too much energy for what it wants. This usually happens because it got hit by a gamma ray, and so now everybody's got a little bit too much energy, right? So they need to get rid of that energy to get to stability, right? Otherwise, too much energy, it's not enough to split things apart, but it's, above where it wants to be. So at some time later, it'll emit a gamma, right? And that's purely just to get down to a more stable nucleus energy level. Does it make sense what's happening with each one of these? Yeah.
A over Z is protons and neutrons, respectively?
Yes. Well, no, sorry, hold on. You mean the A here and the Z?
Yeah.
Okay, so A is your atomic weight or atomic mass, right? Z is your atomic number.
Okay.
And the X here is whatever the name is. So Z and X are tightly coupled, right? So if Z is 6, then X is carbon, 1-to-1 thing, right? A could be carbon 12, that'd be a stable one, right? So we could come down along here, and that's boom, right? And you'll see that 6 and 6, you could see carbon 12 right there, right? It is possible to keep your same Z though, right? This is all column. Carbon in the same column. So it's possible that I could go from carbon 12 to carbon 13, right? Still stable. Carbon 14 is the blue one, right? So that we know carbon 14 is kind of, they use as a dating method because it's well known it's decay. And you can see from this chart the decay that it does is a standard beta or beta minus, right? So beta minus is also beta. It just means it ejects an electron. Does that make sense? Do we feel comfortable reading these now? All right. So that's all this is telling you. This is your atom. And when it goes in here, right, the atomic number stayed this, or the atomic mass stayed the same, but the number increased by 1 of Z. Right? So it goes from X to Y. Right? And you end up with an electron, which essentially does not have a mass, but it's got a -1. They're just saying it's the charge. Right? Yeah, I know. This is probably like, okay, I'm an engineer. I don't really need to know this. But the reality is you kind of do. We're going to use this type of stuff to produce stuff. Right? We need to be able to generate stuff, and so understanding how they work is pretty important. Anyway, I also like this chart. They often don't show them, but I find this very helpful. Right. All right. So let's talk about lovely ionizations. All right. So this is where we actually kind of want to go, and the reason is biologically, this is going to be damage. Right? How dose is going to get kicked in. That's going to be important when we design equipment to do treatment. Right? So medical imaging and medical therapy are really tightly related. Right? Medical imaging, we're trying to figure out what's there, and then therapeutically, we want to apply a certain dose amount to actually induce the damage. On medical imaging, we don't want to induce damage, but you kind of have to. If you don't lay down some amount of dose, you can't image. So this is a really crucial idea to get across. You cannot get an image without some amount of dose, because I have to attenuate the signal. Right? That attenuation of the signal means stuff has to go away. There's a tiny amount you can get rid of, right? A tiny amount of attenuation that's going to happen without causing damage, right? That's with elastic scattering or coherent scattering. We will talk about it, but coherent scattering is like the lowest energy use one that's out there. So unfortunately, it's not really enough to be able to get an accurate image. Right? So to get a good image of what's going on there, we're going to have to push into some stuff that does damage. It's unavoidable. Then what you want to do is get something that does the least damage, right? While still getting the effect across. So this is again why you care about it, because it's a trade-off, and your trade-off is exactly this. So what we're concerned with when we ionize, right? Because ions cause damage, right? How do ions cause damage?
They can steal electrons or give electrons to atoms and break them.
Okay, so I can cause bond breakage and things like that. So imagine that I had, one of these inside my cell. It could go around anywhere it wants. This could bond onto something important and break the bond where it needed to be and potentially separate things out. Right? Anybody know what we call that in common parlance? You've got, they're radicals, and they're just kind of floating throughout your cells, so they're free radicals. Right? So you hear all kinds of people worrying about free radicals. They happen normally. Right? You do get some from the sun. There's radiation that comes from granite decay. Right? I mean, there's all kinds of stuff that are sources of radiation. And we'll get to the minimum amounts to call them dangerous or ionizing in our purpose. But one of the ways in which these free radicals are dangerous is that they themselves bind onto stuff. And one of the most dangerous areas they can is DNA. So we generally like to avoid them being able to affect our DNA, unless we're trying to kill the cell. Right? In which case, if we're trying to kill the cell, right, it could be cancerous, there could be some other problem with it, right? So neurosurgeons will also want to do this if, like, somebody has fibromyalgia, right? So you could have this area of fibromyalgia, it's like a nerve cell that's just turned on way too high as a pain receptor, and so it just amplifies everything. So people in just normal conditions feel like their arms on fire and stuff like that, right? There doesn't seem to be too many good ways at the moment to turn them down. So one of the common ways to do it is just selectively find the ones that are acting up and kill them. Right? In which case you stop the thing that's screaming bloody murder, and all of a sudden life becomes handleable again. Right? You kind of turn it down. There's similar types of things that happens with like Parkinson's. Right? So Parkinson's get worse because cells that currently have Parkinson's influence other cells to start doing the same exact thing. So it's actually can be very helpful early on to kill off some of the Parkinson's cells so that they can't train other nearby cells, thus removing the dangers later on. Now, whether in the long run there's other techniques, this is just what's currently doable now. Right? And the more we understand it, the more we can generate techniques to aid surgeons. But that's another way that goes on, right? This is all from that same idea of radiation ion binding. That's not the only way in which they can act, though. All right? Do you think of any other way they might be able to do something?
Well, some cells have delicate charge balance. Would that affect those?
So it does actually have to do with the charge balance, but it's a little bit more odd in this sense. You have to come back to think, how often do you have ions sitting around? Do ions just sit around indefinitely?
Well, they like to bond with them.
They like to bond, so I mean, eventually they're all going to go away, right? So why are they still here? They should have all gone away by now, right? So why do we still have them?
Don't some ions like help you like maintain? Maybe I'm not thinking the right kind of ions, but like don't some ions like help yourself?
So we do have areas, but why do you have them? Somebody has to. It maybe is almost too obvious a point.
They create like energy gradients that can be used.
So that's what they do. How do I get them?
Yeah.
Yeah. So somebody has to produce it by ripping the electron off. What happens when I rip that electron off? It's got to go somewhere. That's going somewhere with energy. So what happens when that hits something? Remember we just mentioned that electrons flying around can cause decay. They can also bump into other electrons. They might have so much energy, they might be able to knock out several electrons. They've got like a really hard hit billiard ball hitting a tightly packed fruit. You can get a whole bunch knocked out. Right? So when in the process of making those ions can also cause damage. And some of this is natural. It has to happen in the cell in order to work. Some of it is going to be a byproduct of us imaging. Right? So not only will we get damage because we've made an ion, but the process of making an ion will also release a high energy electron that's going to cause damage. Right? Both of those cause damage. Now, is all the radiation that's out there, is it all EM? Because that's what we're talking about so far, right? Now, what else is radiation besides electromagnetic, gamma rays, X-rays, stuff like that? There are. And we just mentioned one, right? That free electron shooting out is radiation. Right? That's a beta particle, right? Beta particle is an electron, free floating, then ejected. Right? So we get beta radiation, which is particulate, alpha particles. They don't travel very far, but they're dangerous. Right? So we have particles and waves. It turns out that when you're dealing with ions, right, and technically an electron is a really lightweight ion in some sense. So when you're dealing with particulate radiation, they're almost more directly damaging than the photons themselves, right? Because they're ionized, they're going to grab electrons, release radiation and everything else. But on top of it, they're going to come in with energy and they're just going to smash stuff. So you're going to have smashing and electron release, and you're going to have, some EM release when it impacts it. So you're going to get a bunch of stuff. So particles can actually be, in some sense, more damaging, right? But none of these particles will do consistent damage based on energy. As you change the energy, the different interactions, rates will change, and that's going to affect the damage they do. So for instance, particles, the more energy you give them, do you think they become more or less dangerous?
More energy is more dangerous.
Sounds reasonable, doesn't it? But it's not true. More energy, less dangerous for particles. You're in mostly empty space. I give you enough energy, you fly through, and you don't have enough time interacting with stuff. So it turns out lower energy particles are actually more dangerous than high energy particles. there are going to be a few weirdnesses like this. Right? To be, this is actually why, so my group is developing a particle imaging technique. One of the reasons is if I give it a huge amount of energy, right, instead of kilo electron volts like X-rays are, I give it into the hundreds of mega electron volts. It turns out the actual dose damage will drop to about 1%. Drops off pretty quick. So there's going to be some trade-offs that go on, and this is going to be depending on what the interaction mode is. Right? When those particles get slower, below 1 million electron volts though, they start doing a lot of damage. Right? Crazy high amounts. So this just to give you some kind of guidelines in your thinking on stuff. All right, so let's think about how we make these ions, and we'll kind of figure out some areas that come out. All right, so I've got a neutral atom. It takes energy to promote some electron, right, out to the shell, n equals infinity. That's free floating land. Often we simplify that as one shell above the last one that's occupied. Right, so if we say valence is your last occupied shell, the shell above that, right, is the conduction band. So we could often do there. Generally speaking, inside the physics area, if you kind of notice, these lines are proportional to their energy. This one is for hydrogen, right? You can notice infinity is really not that far past everything else. So that's why it's kind of reasonable to consider conduction, because you're usually way out there anyway. Now, for hydrogen, you can kind of think of this as the simplest atom. So we use this one as our benchmark. There's only one electron, so this is our ground state. There are a couple other levels that can be energized states. But if you assume your electron's here, it takes 13.6 electron volts to remove that electron completely from the atom. I'm giving us a free-floating proton. That's of any atom for its lowest state shell, that's the lowest energy. I'm trying to be very careful with that wording. There are heavier ions that have a really far out shell, right? And the state for those is sometimes really small to get something out. Like metals often have that case, right? Their top electron is pretty close to being shoved out to infinity. That's why they're metals, they conduct easy, right? Easy to move the electron. But we're going to use this as our reference point, right? Because for most systems, and particularly for organic systems, you got a lot of hydrogen in you. So it's your most prevalent atom, actually. So 13.6 electron volts is what we're going to call the break point between ionizing and non-ionizing. So if you have a wave that has less than 13.6 electron volts, it is non-ionizing radiation. If it has more than 13.6 or 13.6, we call it ionizing radiation. Anybody know about where 13.6 falls?
UV.
UV. Yeah, it's pretty close actually in the UV spectrum, but it's UV. So this isn't too surprising, right? When you deal with radiation damage, what's the most common radiation damage people will know of? Sunburn, right? And we know sunburn eventually causes cancer, right? So we know this is there. And so this kind of gives us a good feel that this guideline actually makes a lot of sense for what's going on. And that's actually why it is causing cancer, right? Is because it's repeated damage from this radiation. Is cancer a bad thing, a good thing, a misunderstood thing? What is it? Just in general. I mean, if you get a cancer diagnosis, you're pretty unhappy about it. But from biology standpoint.
Well, the cell's really a mutation, right?
Yeah, and the cell is really quite happy, actually.
And all those children are really happy too.
So what is it? Why does it exist?
Rapid cell growth.
It is rapid cell growth. So why would I need rapid cell growth? why it was repaired, right? It's meant to be turned on and off, right? Cancer is when the turn off mechanism breaks. So it just grows and grows. But when you get too much damage, right, your body's response is, I better make some of the cells just crank out replacement cells to fix this. So it is really your body trying to go into this high repair. But sometimes in going into that, our system breaks. And it goes into the high repair mode, and it just never comes down. So it just grows uncontrollably. Well, that's non-sustainable. So then your repair mechanism has got all whacked out.
So like the alcohol that damages your liver.
Repeated damage bad. Yeah, repeated damage bad. No matter what you do, this is, and there's a lot of reasons for this, right? You know, I'm really simplifying a lot of stuff here, but it's a true point, right? Damaged cells do several things, right? Not only do they try to move into this hyper area, and the more you do it, the more likely something breaks while doing that, right? But on top of it, whenever I feel damaged, right? Imagine each of us as a cell, right? And you get damaged. What are you going to do? Right? You're sitting there, all of a sudden, you know, somebody drives by and shoots in and you get shot. What are you going to do?
Die.
Let's say it just shot you in the leg. Right?
Yeah, you're going to scream.
Yeah, right? Even if you die, you're probably going to splatter blood everywhere. So, you know, not to be grosser. But what are you doing when you do that?
Making a scene.
And you're warning everybody else.
Yeah.
Right? So when a cell gets damaged, guess what it does?
It warns everyone.
It warns everybody else. It tells you, you better get into that mode. So not only does the cell that got damaged go through this process of ramping up, the other cells nearby go, I'm next.
Yeah.
So they start ramping up in response to these type of areas. That's often why even if we treat a cancer and we kill the cancer completely, a new one grows back in the same area because the nearby cells got signaled. Right? They've actually done tests where they've taken cells that were nearby where something was treated, removed them, put them in a healthy area, and secondary cancers grew higher rates in that area because the cell that was exposed to the problem told everybody else it's a problem even after it was all done. Right? So this becomes kind of an issue. And part of that signaling is they got hit by radiation. So that's why we have to be very careful doing minimal dose. That's why it's important to make dental x-rays that have lower dose while still maintaining good image quality, so on and so forth, because we want to avoid that repeated process. That make sense? So, and realize it really is just this ionization. When we talk about dose, all it is energy per unit mass. Right? You release a certain amount of energy in there in some mass area and away you go. So I kind of put this on so you can kind of view, see the ionizing red line? Just past purple, right? So that gives you your ultraviolet. Notice what's in there, right? Also tanning boosts, right? Things of that sort. Medical x-rays, any radioactive source. Right? Coming down to other areas, these ones are non-ionizing. So that means they're completely safe, right?
So hydrogen
They're not ionizing, right? But that doesn't mean they're completely safe. Many of them are safe as far as we know. But there are some, for instance, right? Microwave. What does a microwave do?
I want to stick my hand in a microwave.
Yeah, you know? I mean, if somebody tried to, there is a famous case, I've been told it is true, that somebody tried to dry off their pet by sticking them in a microwave. This was in the 80s, and they had just come out. And so the story was it was an older person who didn't understand. And that's kind of tragic because, you know. But my point is, why did that happen?
is water has resonance in the microwave region.
And you're inducing a thermal load on it, right? Some of it is a current induction, some of it is it just creates more energy, so there's, even though it's not an ionizing amount, you just add more and more energy to the cells. Yeah. So it will actually do it. You can actually create burns from infrared also, right? So that's another case where I can do it, right? Infrared is sometimes called heat lamps. Put too many heat lamps on, you're going to induce a burn, right? I mean, infrared cooktops are very popular, right? I'm not saying anything against them, but they're cooking things, and it's non-ionizing. So ionizing isn't the only area that's problematic. Now, are there some areas that we know of no problems?
Radio waves.
Yeah. Actually, below, probably about here, right? So cell phones, in general, when people say, oh no, the cell phone's cooking my head, probably not. There have been extensive, probably more extensive studies on that than anything else, and nobody's ever found a problem. And they really are pretty darn extensive, because the FDA required a lot of stuff, and Apple and other people want to sell things, so they'll do whatever is necessary to be able to prove they're safe. So they've conducted really heavy things, and nobody has ever seen a problem. So the likelihood of there being a problem is small, right? So you're probably pretty small here. There are some radar and microwave stuff can be. Right out of my master's degree, I worked for Northrop Grumman at a military base, and we had a radar testing thing. And when we fired up one of our planar arrays to be able to test it out over the water, seagulls that flew through it would die before they hit the end. They literally cooked them, right? So you would watch them fly in and, and that was airplane mounted ones. So you can only imagine what happens with large ones. That in my first, but then it gets overall fairly safe again. There is a little bit you can do with the infrared, like I mentioned. Infrared, there's actually a neat technique for us even that utilizes infrared on this. So infrared puts out heat, and this is actually one way, so University of Arkansas has been working on this. Cancer cells are larger, and so they have a higher metabolism, so they'll absorb more energy. It's one of the features of them. So if you expose them under infrared, they'll take more and they'll start vibrating. So they've actually got a system where you put it on a blood vessel, and you run a constant level, and when cancer cells go under them, they oscillate, and you put a photoacoustic system on, and you can hear the cancer cell pass by. And then they turn up the infrared at that instance, and they just get a PID system. So when the acoustic gets to a certain level, and they just pump it really high, and a cancer cell is going to absorb as much as it can. It wants energy, right? So it actually gets so much energy it bursts. So they've actually got a system that treats cancer with infrared, right? So I'd say there's a little bit of a danger zone that goes from about here right to the edge, right? Again, then it's safe, and then it's just all dangerous after that. So that's kind of, when you're thinking about the spectrum, that's your danger spectrum. Does that make sense? The other thing you want to think about is penetration, right? So this one is just to give you an idea of how much can go through. Alpha particles, right? Really heavy nuclei, paper stops. They don't go far, right? Usually when you hear problems with this, back in the Cold War, probably 40 years ago or so, there was some decay of heavy ions and that, and the Russians were famous for putting in people's drinks and things. And these alpha particles would get emitted after you drank them, and they're inside your body now. That's bad, right? Because it doesn't have to go through much. The only thing around there is you, right? So as they get absorbed into your body, they go all throughout your body, and alpha particles emitted. So it may not penetrate through the paper, but dang does it hurt the paper when it does it, right? This one shows a lot of these, right? You can see X-rays go less than gamma rays. Where's ultraviolet? How much would it take for ultraviolet? Yeah, paper actually stops ultraviolet. Right? So that's why when people are trying to use ultraviolet to clean desks and stuff, if you have a piece of paper on top, it won't clean the bottom side. Because it can't penetrate through. Right? So, ultraviolet would be like alpha particles stopping there. Beta, the electrons, will be stopped by a thin piece of aluminum or wood. Aluminum is actually often the standard we'll use. So most states are going to specify a beam quality. We'll talk about beam quality next time. But they'll specify beam quality by a thickness of aluminum that it has to be able to penetrate through. That becomes really important to us because low energy stuff, right, actually tends to be not good for you, right? Low energy is all absorbed and none of it makes it through to image. So it's all dose and no benefit, right? So we don't want low energy stuff, right? That becomes kind of a big issue to us. How much can you penetrate? So aluminum is particularly important, right? By the time you get to like lead, the only thing going through those are neutrons, right? There's also some cosmic particles too. But that's why when you have neutron, usually you have thick amounts of concrete, water, or stuff like that. So anyway, for most of our area, this is the one we're gonna care about. Because most of our stuff, X-rays will go through it, but it depends on how much energy, how much of it will go through. We feel good? Okay, one other thing. I promote this all the way up. Right? So I get that electron out. That is your basic photoelectric effect we're going to deal with. Right? Something else is going to fall back in. Right? They could fall back to ground state, they could fall back to n=2, and then eventually fall down from there in. Right? As it falls, it gets a certain amount of energy. Right? So like for instance, the Balmer series, if I come from infinity down, I'm going to get 3.4 electron volts. Right? So, that's more in your infrared red zones, right? Down to 13.6 if it falls all the way. That gives you ultraviolet coming off. That's an emission. So depending on those fallbacks, you will get radiation that comes out naturally as electrons refill. And we call that characteristic radiation. Okay. So we feel good about ions? Okay. Quick stuff on particulate radiation. Have all of you at least seen, or everybody's at least heard, right, the famous stuff, right? E=mc², things like that. Is everybody familiar with Lorentz factor? Right? 1 over the root of 1 minus the ratio of your speed versus c squared. Right? So your relativistic mass is just your rest mass times your Lorentz factor. That's probably the easiest way to remember it. When you get, the one area we care about this is, when you're dealing with very high energy stuff, you can't use our standard kinetic energy assumption, right? 1/2 mv² is only true when v is small. It is not actually generally true, right? It's only true for low energy, low velocities. When it gets to high energy, you have to use relativistic. Now, it turns out relativistic still works at the low energy. It's just more complicated, so nobody wants to use it. Right? So when you're dealing with it, the real way to understand it relativistically is the total energy is the rest energy. Right? And the rest energy has to do with your rest mass. Right? If I were to convert that rest mass into energy. So this is where the famous E=mc² comes in. So that's your mc². It comes in. Your kinetic energy is this Lorentz factor, right? So I take the Lorentz factor minus 1, right? That quantity times, your mc². And again, that's still that same mc². The Lorentz factor is going to turn your m into m0. Right? So your kinetic energy is the difference between your rest state and that total energy, and that's actually what this one calculates for. Right? So if you think total energy is Lorentz factor times it, right? And the rest energy is just your regular mass times c squared, right? Therefore, the difference between your total energy, lambda mc squared, minus mc squared, that's going to give you your kinetic energy. It turns out when V gets small, that just reduces to 1/2 mv squared. Okay? Let me ask you why. Why would you believe that's true? There's no half. Right? So where the heck does the half come from? Give it a sec to think. I'll tell you why, but I want you to at least give a try. Otherwise, it just becomes me telling you boring facts.
Integrating momentum.
Okay? So why would that give me a half?
Well, if power rule would divide out the square to half.
Okay, so we got to think, it does have to do something with powers. So think about the equation that's going on here, right? Gamma minus 1. MC squared is pretty standard stuff, right? And eventually you're going to get MV squared. So it's kind of in the right form. So the weird thing is that gamma minus 1, right? And this is gamma. Is this pretty? Is this easy to deal with? What might happen as V gets small?
You can increase the denominator with a decrease.
So as V gets small, what happens to this term? It goes towards 0, which means this whole thing's going towards 1. Right? So the question is, now that observation doesn't tremendously help me. Right? So the question is, how fast does it go towards 1? Right? That's what you learned in calculus. It's not necessarily that, it's how quick things are going there. Right? So square roots are ugly. So what might I do to get rid of that? What's that?
Rationalize it? Or, yeah.
So how can, I want to simplify it. I want something I can substitute in the place that will be exactly it in the limit. And think about your powers, bunch of terms. Taylor expansion. Right? So what's the Taylor expansion of square root? The square root is a half. So you get a constant plus half your next term plus, right? If it's very small, you only need to take the first term, the 1/2. So you'll get a 1 and a minus v squared over c squared. And that's going to then come in and you've got a c squared, which will cancel that part out and you'll be left with a v squared. Right? And that will be on the top. On the bottom, you'll still have a v squared over c squared, and you have a v squared on top. And the v squared over c squared on the bottom is going to go to 0 and drop off. Right? So that's basically why the half term works out, because it's actually the Taylor expansion. Right? So it's really straightforward once you do it as a Taylor series expansion. This is where some of that stuff's going to come in real handy. Right? So what you want to get used to, the whole point of this is just to make you start looking at these and say, hey, look, I see some of these. Whenever you hear a result, don't believe anything. Right? Especially because it's true. Right? Because how good are you at memorizing facts?
Not amazing.
Does anybody here feel they're amazing at memorizing facts? There are a few rare people. Right? I suck at it, I'll fully admit. Right? But if you know why, I guarantee you remember it a lot longer. Right? So if you understand the idea behind it, that's why it's going to carry it. That's the big part for these. So when you see the answer, because it's true and it's going to matter in the future, and it will only matter 5, 10 years down the line, you randomly get hit with this type of stuff, and all of a sudden you have to do it, and you're like, oh my gosh, I forgot everything, right? That's where if you basically had an idea why, you can rebuild it. And you can also know what to search for, in Google and everything else. If you don't understand the idea, it's really hard to search for what to do. Right? Google is great for searching for facts. It is not good for searching for understanding, because you have to understand to be able to search. So if you have understanding but lack the detail, you can always find it, but not the other way around. So this is why I'm really hammering on this one, because I want you to remember the ideas behind it. You can look the stupid formula up. Right? Do we feel good about this when it comes in for particles? Most of your particles, by the time we accelerate them, so for instance, the book gives an example of an electron, is going to be used to release X-rays. And we do that by accelerating them, usually over 100 keV voltage potential, right? Or 100 kilovolts, right? 100 kV. That's 100 kV is a really large voltage. By the time that electron hits the end of that field, it's traveling probably close to about 20% the speed of light. You cannot ignore relativity at this point. Right? It's traveling too fast when it slams in. That's why we get the high energy X-rays we need out of this thing. Right? But if you try to calculate that off of just standard calculations, it's going to be wrong. You will not get the correct amounts. So that's why this matters. All right. I mentioned to you here, because I'll mention it several times, the rest mass of an electron, 511 keV, because it does come back in a number of weird areas. Okay. You're probably all pretty familiar. I'm going to blow through this slide fast, because as electrical people, if you know anything, you gotta know this, right? But remember, E equals H nu, right? So this is your energy basically related to your frequency, which you can translate to your wavelength by the next equation, lambda equals C over nu. Okay? Those two are the important ones with the appropriate constants that are on here, Planck's and obviously the speed of light. I just reproduced that one just as a mnemonic rememberer again. Right? So remember, electric field, magnetic field, orthogonal, the direction of travel, right hand rule. So everybody gets used to doing that lovely hand position and twisting. Yes, right? So you can tell physics people. Everybody know why right hand rule? Besides the fact that it works, but where the original one came from. Quaternions, 1800s, actually before a lot of this came on. Hamilton, the famous mathematician from Ireland, was working on square roots of -1. And quaternions are where there's 3 square roots of -1, I, J, and K. Right? And so that's your 3 fingers, and they point in different directions. And that's why quaternions became a thing, because they actually give you the physical universe. And multiplying 2 quaternions gives you 2 different things. One half of it that deals with the quaternion part is called the cross product. And when you deal with the real component, the 4th direction, that falls out, is called the dot product. And so when you have 2 matrix products, if you wonder why when you do cross product, you have that weird IJK across the top, that's the quaternion directions. So that's actually just a matrix attempt to interpolate the idea that just flows out from right-hand rule. Anyway, so that gives you your wave area, right? I'm figuring you're all fairly comfortable with this. Just don't forget the relations, because you got to calculate a lot of stuff with them. All right, so I want to talk about scattering real quick. Is everybody familiar with at least some amount of scattering? Right? So how about the first one, coherent, right? So coherent, there's no energy loss. That's Rayleigh scattering. Anybody know what Rayleigh scattering is? There's a great example of Rayleigh scattering. Why is the sky blue? Rayleigh scattering, that's why. Right? So it's coherent scattering, that's what makes the sky blue. Okay? Deal with that on the next slide. Incoherent, you lose energy. So the idea with coherent energy loss is the photon doesn't lose energy. Right? Energy is never lost in the grand scheme. We're talking from the photon's perspective. Right? So the photon in coherent stays the same. It just gets scattered. In all the incoherent ones, photoelectric Compton, pair production, things of this sort, which we'll deal with, these are the ones that are going to turn out to be most visible to us. All of those ones are going to end up being ones at which our photons will lose energy. But you kind of want them to lose energy. You're slowing things down, you're removing them, right? So that's a good way to figure out that, things haven't made it through. Okay, let's just talk real quick. With Rayleigh scattering, you're basically assuming light is coming in. It energizes an electron, but it's not enough to promote the electron to a new level or to kick it out. All right? So that electron is just energized. It doesn't want that extra energy. It doesn't fit nicely in its quantum shell. Right? So it goes around a little bit, decays, emits the exact same frequency because that's how much 2 energy it has. Right? But it's kind of a different place than it was before, so it shoots off in a random direction. Right? This is proportional or inversely proportional to your wavelength, in particular lambda over 4. Right? So if you think the intensity of this scatter, how much light is affected, is reciprocal with lambda over 4, will it affect red or blue more?
You said it was inversely proportional.
Right? Intensity, proportional 1 over lambda,
So
the 4th.
it affects red more.
Okay, so what is red's wavelength compared to blue's? Which one is longer? Red. So if I have a bigger number down here to the 4th, that's a really big number. 1 over it is really small. So the amount of intensity affecting that goes into the scatter is really small. So this intensity is how much scatter intensity you're getting. The bigger that number, the more scatter.
I interpreted your question, which frequency would change your incoming more?
Yeah, which one's going to be scattered more?
Right. So I think I was thinking, if you were to compare input and output, which one is more different? And
So which
that-
one's,
that would be
this intensity is not the input output. This is the amount of intensity that's scattered,
right.
right? So you have the input intensity, and then some of it goes all the way through, and some is scattered. But the part that goes through plus the intensity that's scattered is what came in, right? So as the scattered intensity, maybe I should have put a sub S or something, right? The scattered intensity, if the scatter intensity is bigger, more stuff is scattered, right? If the scatter intensity is smaller, then it's telling you more stuff was not scattered, right? So more things unaffected. Does that make sense? Is it a distinction? So this is why it's blue, because blue is a shorter wavelength. So a smaller number to the 4th is going to have a larger intensity that's scattered. 1 over something small is big. Right? For red, it tends to be very small. So that's why it takes until you're going through a very thick atmosphere for it to become large enough for you to see it. Hence why sunsets become red. Does that make sense? So the proportion for attenuation ends up being the larger the atomic number, right? Basically, the bigger the thing you're running into, so it's going to even have a bigger mass, but it tends to be proportional to Z, the number, which is the number of electrons in some sense, available to take that energy and scatter it. As I get bigger and bigger ones, I'm more likely to be able to grab it. So this goes up as the atomic number of whatever you're passing through goes through. Right? This is the attenuation coefficient, how likely it attenuates it. Right? So bigger Z means more attenuation. If the energy of the photon goes up, it's more likely not to be bugged by it. So if you have more and more energy, you get less Rayleigh scattering. Right? That's the general relation, assuming all other things are equal, right? For attenuation of what makes it through. Now, this is actually why it doesn't matter very much for us, because most of the other terms we're going to deal with are going to be like z cubed or z to the fourth. The z is bigger than 1, well, or at least equal, right, with hydrogen, but for an awful lot of our stuff, it's going to be bigger than 1. So high z powers are just going to be bigger. So this one is going to be a smaller coefficient pretty much for everything we're dealing with. It's at most going to be, less than 10% of the total amount of attenuation. That's why we say Rayleigh scattering is not a big issue to us. But this is the one that by and large doesn't do damage. So, but it will do a small amount of areas. Photoelectric effect, right? I might have to finish some of these off next time. Right? Everybody know photoelectric effect? An electron is going to absorb the energy, get promoted out. That's only half the story, though. Right? We already mentioned that some other electron is going to fall down, depending on where it comes from. If it falls from really far, we'll get 1. But notice they're in a tight band, that grouping. Right? There's a different group here. If it falls from here, you'll get a different characteristic energy. So you'll get these kind of characteristic band peaks that kind of show these electrons coming down. There's also sometimes, instead, this will fall down to the empty shell, and it releases the radiation, just like this one did, but that radiation goes up and hits a different electron, right, and knocks it out. We call that an auger electron. So you can end up knocking out more than 1, right? You knock out the first one, photoelectric, right? Somebody else falls down, releases a photon. That photon strikes one as it's about to leave and knocks that one out instead. So you tend to either get an extra electron that's fairly weak, or you'll get some radiation. That radiation is going to move in a random direction, and it won't hit the detector. Right? Very low likelihood that it hits the detector. That's why it's a loss. Right? Photon going that direction, not absorbed, turned into something going a different direction. Right? Different direction, thing doesn't get seen. Therefore, a loss. Right? So either the auger electron or these characteristic ones, in general, will not tend to produce stuff. Right? So probability of its effect is z to the 4th over e cubed. Right? So you can see much higher than what we're getting with our characteristic. And the actual attenuation effect will be z cubed over e cubed. Right? So how many photons are lost on it. All right, we feel good with this. We'll pick up with content scattering next time. But hopefully this is reminding you of some stuff and building some intuition. Okay, good deal. Constant.